Okay, so let's first look at something we covered towards the end of the last one, which was the isothermal. Well, it wasn't the isothermal, it was more the energy balance. So we looked at the energy balance in general, and we started all the way back from looking at the rate of change of the internal energy in the reactor in terms of the entry of energy. So just because a stream was entering the reactor and carrying the species coming in carry a certain amount of energy, and there's a certain amount of energy going out. And then and this balance is actually incorrect because you would not separately add the heat of reaction term. So that really results from the difference in energy between these two. So in the notes, it says this is incorrect because that term is like double accounting there. So we developed this balance, we accounted for the energy changes, and we accounted for other forms of energy, shaft work done on the system, heat added to the system as well. And so we developed the energy balance of this form, right? So we combine that with the overall material balance. So the earlier work on isothermal reactor design, all that was incorporated until we finally got ourselves the energy balance, which looks like this, right? So earlier we talked about the flow in and the flow out. So the flow in minus the flow out, that's not these terms. I shouldn't have been pointing like that. So flow in minus flow out is also equal to the energy that you get if you compare the enthalpy in and the enthalpy out and the amount of energy that has been transferred. So if you like, these are two different ways of counting the energy. You can simply, if you can imagine someone standing at the entry to the reactor and counting up the energy going in, and then someone standing at the exit of the reactor and counting the energy going out there. That's one way of counting the energy. Another way of doing it is to just think about all the fluid that flowed into the reactor and ask hypothetically, if we compare the temperature T in and the temperature T out, and looking at everything that enters, if only the temperature changed, then you will get a certain energy change. That's not actually what we accomplish in the reactor, because what comes out is not the same molar flow rate as what's going in. So what actually comes out depends on the reaction and how much has been converted. And so the hypothetical energy due to a temperature difference plus the heat of reaction, that must equal the same as if you look at the energy coming in and the energy going out. So this balance is just a different way of counting up the energy across the reactor. So that's our energy balance. And something to point out in this balance is that this does not depend on the type of reactor at all, right? If you go back and follow each of the steps, at no point do we use the assumption of perfect mixing. At no point are we saying that there's no flow in or flow out, right? There are flow terms here, but those flow terms could be zeros. We are not saying that the fluid needs to be completely segregated and flow like plugs or anything like that. So this balance, if you like, is purely about the chemistry. It's not at all about the flow through a reactor. This relationship, this energy balance, it's a relationship which is intrinsic to that chemical. So the point of saying this is that we can rely on this balance for every type of reactor. It is always true. And that's why we'll use the same balance again and again in the different reactor types. So you looked at some examples on counting up the heat of reaction, and then we started to look at the addition of heat. So up to that point, we hadn't worried too much about the Q dot term. Now we are interested in the fact that there might be heat exchange between the reactor and the surroundings of the reactor. And this can happen in different ways. So for example, if we have a CSTR, right, your CSTR will have its own temperature on the inside. So call that T. And then if you have some other heat exchange medium, so let's say there's a cooling jacket around here. So there's a jacket around this reactor, and there's a flow of some heat transfer fluid through this jacket. So it might be cooling water that's circulating in the jacket around this CSTR. So there's going to be a certain other temperature here, so temperature in the jacket. And this temperature may vary across the jacket. You can imagine the cooling water enters at a certain low temperature here. As it's exchanging heat with the reactor across the walls, its temperature will rise. And so the exit temperature on the jacket might be different to the entry temperature to the jacket. But of course, if the flow rate through the jacket is high enough, then that temperature increase might be small. So there's another set of energy balances that we can write on the jacket itself, right? So as the fluid is flowing through the jacket, its temperature is changing. And the real interest to us is how much energy is leaving the jacket and entering, how much energy is leaving the reactor and entering the jacket. So that's the Q term of interest there, right? So there's a certain energy transfer rate between the reactor and the jacket. Okay, so that is something that can be estimated, not by developing some kind of new theory, even though reaction is involved and it's in the context of a reactor and all that. By the end of the day, it's a simple heat transfer question. And so all the development that you've seen in the heat transfer course, all that applies here. So we can define some overall heat transfer coefficient between the reactor and the jacket. And you will recall from the heat transfer course, you've got your, you can think of it as an internal film here, and then there's a conduction across the wall, and then there's a certain other film there. And by the end of the day, there's some overall heat transfer coefficient that summarizes all of that. So you've done all that in heat transfer. So that all goes into estimating your U. Your contact area, of course, is going to be this contact area, this contact area between the reactor wall and the jacket. And then there's a certain temperature difference. And this temperature difference, as you know from heat transfer, is not necessarily an easy thing, right? Because if your temperature here is different to the temperature here, then the difference in temperature between the reactor and the jacket, that is different at different points across the space. However, we have clever ways in heat transfer to figure out the average temperature difference across all of that space. And so you get log mean temperature differences and things like that occurring here. So the point is, we are able to estimate the amount of heat being transferred between the reactor and the jacket, especially if we have some indication about the jacket temperature. And again, if your jacket flow rate, if the cooling water flow rate here is high enough, we can simplify the jacket temperature to be similar to the inlet jacket temperature, TJ in, if you like. And then in the reactor, if it's a CSTR, we know there's one temperature that applies everywhere there. So all of that goes into estimating Q dot. And of course, the temperature in the reactor, it is also affected by that Q value itself. So in the energy balance, I'm just looking for it quickly. So in our energy balance here, I've lost it. Okay, anyway, here. So in our energy balance, we can estimate Q, but this Q may involve a temperature, a reactor temperature, which is also the temperature here. So temperature arises in this balance. Sometimes we don't exactly know what the temperature is in the reactor. It's something we have to solve for, and it appears in two places. And it's a little bit hidden here because there's this integral. So your reactor temperature actually occurs here in the upper limit of this integral. So just remember that when trying to follow the developments, you've got a hidden reactor temperature over here. Right, remember the exit temperature from a CSTR is the same as the interior temperature. So that's all there. And then shaft work is normally an easier thing. We don't need separate balances for that. We normally know that if we are applying applying stirring action, then there's some motor here that is applying that stirring action. And we just look up the power rating on this motor. And then that tells us the amount of shaft work we are doing on the reaction mixture. Sorry, 1 second, please. Sorry about that. Okay, so shaft work we can easily estimate over there. And so overall, we can define these two terms. And so those are kind of new to us. All these other terms are things we've dealt with. And if you've done those exercises on estimating the heat transfer and the energy, and you've done this lots of times in, I guess, thermodynamics and heat transfer. So all of these can be estimated. So hopefully it means that when you look at this balance, you should have some confidence that you are able to solve this balance, that if if we have all these quantities identified, then we can solve this balance for whatever variables are not defined. Another thing to think about with this balance is that it's giving us a relationship between X and T, right? So you can see conversion is here, and we mentioned T is here and here, right? So, and of course here. So this is in effect a relationship that we can write. Let's just write this. So by the end of the day, the energy balance is giving us something like this. Your conversion is a function of temperature. The other thing, the other thing you can think about with this balance is that it's in effect a line, right? If you look at this, this is in the upper limit. If heat capacity is approximately constant in temperature, if that's approximately constant, and that's a fairly reasonable assumption, this is basically the equation of a straight line. So if, well, we'll talk about different conditions just now, but it means that if we vary the temperature, or as the temperature rises, your conversion can change linearly, approximately linearly with temperature. And the slope of this line does depend on a couple of things. Number one, it is dependent on the heat of reaction, whether that's a positive or negative number. And of course, it depends on your heat capacities and so on. But we'll see just now that if the reaction is exothermic, then your temperature increases as your conversion increases. And let's think about that. If we think about, let's say, a batch reactor, as your temperature, or let's think about an exothermic reaction, right? As your conversion increases, right? So let's say this is the reaction. A goes to B. Let's just say A goes to B. And this is an exothermic reaction. So an exothermic reaction. So of course, as more of A is converted to B, the conversion is going to rise. And as A is converted to B, more energy is given off to the environment. So we expect that as conversion rises in this reaction, your temperature will also rise, right? So that's what we expect for exothermic. And then for the opposite case, we can imagine that if this was endothermic, then as the conversion rises, then heat is removed from the environment and the temperature goes down. So for the endothermic case, we would get the opposite effect. Right. So that's the relationship between conversion and temperature. Again, this is independent of the reactor type. I was talking about a CSTR and kind of interchangeably talking about a batch reactor. And that's because this is all purely dependent on the chemistry. So it's a feature of, it's by the definition of endothermic and exothermic, these relationships exist. The other thing to think about is that different points along these along this line, let's say, refer to different extents of reaction. And so you could think of these as different steady states. So if you have a steady state here, right, you could reach a steady temperature in, let's say, a CSTR, and that would be the steady conversion as well. Alternatively, if this was in a PFR, then the same would be true, but you would then find different points along that CSTR. So you could say, well, near the inlet point here, I'm down here where conversion is very low. And then as I look at further points into that reactor, I get a different conversion, a higher conversion. So maybe a conversion up here. And then that will give me a different temperature here. So the temperature here would be different. And so the temperature will change down this plug flow reactor. Equivalently, if we have a batch reactor, so let's just draw another one here. So in this batch reactor, if we are thinking about what's happening in time, so as time is passing, we know the conversion, initially the conversion was 0. So the conversion was 0, but over time that conversion is increasing. And then if it's an exothermic reaction, the temperature will also increase. Right? In this case, it isn't there isn't a steady state, but we can identify different points on this line, and we can estimate what the corresponding temperature and energy will be. In this case, unsteady state case, we do have to revisit the balance. I think the balance we were looking at there was for the steady state. So if you go back and look in the notes, you'll see we got this from steady state. In the unsteady state mode of operation, there may be other effects to account for. But generally speaking, if there aren't too many other things going on in that batch reactor, you will be able to identify some relationship like this that will help you here. Right. So the other thing to think about is that in the batch reactor, the variable T is related to what goes on in the plug flow reactor. It relates to it through the velocity. So you can use the velocity to say 1 meter down the tube or 2 meters down the tube is effectively 1 hour later in the batch reactor or 2 hours later in the batch reactor. So that's the value of this energy balance. You can start to use it to get some idea about what the temperature is going to be at different spatial positions in the reactor or different instants in time, or at different extents of conversion. Right, so that's the value of this energy balance. And you'll see just now in the design side, we use this as our operating line. So we think of this as the line that tells us how our reactor is designed. When we create this reactor, we choose a particular volume. We say this is a 50 cubic meter reactor or 60 cubic meter reactor. So as we choose different sizes, that will change the space-time in the reactor, right? Remember the space-time, it's the velocity divided by the volumetric flow rate. So V over Q, right? So the average time spent in the reactor will increase as we increase the volume if your volumetric flow rate is constant, right? So if your flow rate here is constant, as you increase the volume, it takes more time to pass through that reactor, right? So as tau changes, as the volume changes and tau changes, you are going to accomplish different extents of conversion. And so as your conversion changes because you've changed the volume, then the operating temperature in that whole reactor changes as well. So you see the energy balance is intimately related to the operation of that reactor, right? The energy balance actually determines what's going to happen in here. It's going to determine what the conversion and temperature is going to be. It also means that other things that affect the temperature are going to affect the reaction rate and the conversion, right? So we'll see all that in the design side of it. So the balance here is just modified for the presence of the heat of, if you have heat terms, so your Q term appears here. If it's an adiabat, so in an adiabatic operation, you aren't adding heat to the system, then this term goes to 0 and it's simply this operating line. But if it's not adiabatic, then you have that term in there. So that's all straight from the balance. Okay, and in this example, we were just looking at different approximations. So if you apply the approximation that the cooling water flow rate is high enough, then you look at when you do and when you don't apply that approximation, and we find that they are fairly close. Okay, so that so hopefully you've worked through all these notes and you've looked at, for the CSTR and for the PFR, all these relationships. Right. In this case, we are looking at the PFR, and we are taking a step back, and we are saying if we are interested in different lengths of tube, right? So in the PFR, you've got the design variable perhaps being the length of the tube. So if you want to know, should I produce a 1 meter tube or a 2 meter tube, then it comes down to what do we want the exit conversion to be. And so we can answer that by applying our energy balance and using the relationship between X and T. We are able to use that together with the mass balance. So here's our mass balance, right? And this is an important point that we should have talked about from the beginning. In our mass balance, up to now, we've treated the reaction rate as if it was a constant, and specifically the energy, the temperature dependence of this was basically ignored. So let's write this equation out here. Fa naught dx dt equals RA. And RA, let's say it's a second order reaction, right? Just arbitrarily, let's say it's a second order reaction. So it looks like this. And now you see you have this kinetic rate constant as well. So if we expand on this, we should be writing then that K as a pre-exponential factor and X of minus E over RT, right? Just assuming a simple Arrhenius expression expansion for K, right? So when we look at the balance now, we realize that we have both X and T here, right? In fact, we should be expanding for CA as well, right? So there's a CA here, which we know we write normally as CA in times 1 minus XA, and all of this needs to be squared. Right, so this term as well. So you see now, to solve this balance, we have two unknown variables. We have X, right? So we have X, everything else here is constant. We have X and we have T. So both these variables, we in principle don't know how to solve this. We can't in principle solve this because this is an unspecified function. But now we also have the energy balance, right? This is purely the material balance. So in the isothermal case, where we can assume that we know the temperature and it's fixed and all that, we can go ahead and solve this. But in the case where we know the temperature might change, then one of the relationships we can apply is the energy balance. So again, that relates for us X and T. And so we can rewrite this T in terms of X. Right? So if we apply the functional dependence of T on X, then this equation becomes purely in terms of X, and then we can solve it. Right, so the energy balance makes it possible to solve our material balances. even when the temperature is changing, right? That's in effect what we look to it for, right? We still want to solve our material balances, but we want to relax the approximation that the temperature is constant. Okay, so temperature doesn't have to be constant anymore. That's what you should take away from the energy balance, right? We can still do our reactor design, even if the temperature is changing. Any questions or comments there so far? Okay, so work through this energy balance carefully. Be sure that you can do all the things it mentions here. And now let's think about something quite interesting, which is our reactor design. Right, so in notes 4, we talked about isothermal reactor design, and we had all these interesting graphical ways of figuring out where to optimally choose our CSTR volume and things like that. Now we want to continue with this kind of tradition of these nice graphical methods, this time in the non-isothermal context. And before we start that, let's think about what we are trying to do, right? Besides having fun with drawing nice balances, let's think about that there are certain regions where that we need to avoid actually in our design. Number one, we want to operate this reactor at a nice high rate, right? So in fact, a way to start thinking about this is to remember that when we were doing reactor design in the non-adiabatic case, in the isothermal case, we were always trying to look at how do we get the rate up, right? We are worried, okay, conversion, if it's high, then the concentration is low, then that means the rate is low, and then we had whole methods all based around trying to get the rate up so that we could get the volume down. Right now, we are going to have the same interest here. And now we want to look at this for the case where we may have equilibrium. So before we were quite, we took quite a simplified approach. We were only looking at things like A goes to B. But in reality, all reactions have an equilibrium. All reactions will reach a state where the amount of reactants can live comfortably with the amount of products. And let's think about that, right? While I type this here, can you tell me, is that a good thing or a bad thing? Right, so when we have a reversible reaction, right? Equilibrium, is that a good place to operate? Do we want to operate at equilibrium? Any takers? All right, thanks, Samishka. No, right? Any reasons? So while you are maybe typing your answer there, I'm going to write this balance. So you've said conversion not high enough. Well, think about it this way. Think about writing out the rate of change of component A. So component A disappears in the forward reaction when A goes to B. So A is disappearing here. And then you get back component A when B goes back to A. So you can say here, plus KR times CB. Right, so when you are at equilibrium, you will reach a steady state in A, which means that the net rate of production of A is 0, right? Your forward reaction is still happening, but your reverse reaction is also happening. And that's the part you don't really want. You want lots of product, but the product is being converted back to reactant. So Zuaira says, no, because there's no change, everything is sort of balanced, right? That's right. So you've got your forward reaction balancing with your reverse reaction. You don't want that. You want to get all this product out there so that you aren't producing reactant again. So another way to think of it is, this is the state where the net rate of reaction of A is a 0. And you don't want that. You want to react all your reactant out, as much of it as you can. So, so you want to avoid this the situation where your net rate is 0, right? So if you like, this is a kind of constraint on ourselves. We want to, it defines a state that we need to avoid. So if we want to avoid it, we then need to figure out where that state is. So to figure that out, well, we've got this balance, which actually gives us a good way forward, right? It's given us this relationship, and we should specify that this is a special condition, right? It's not generally true. Generally, that's what's true. But at the state where it's 0, then we are in effect at equilibrium. So we can do this separately. So we can say this thing, this rate of change at equilibrium equals 0. And so at equilibrium, we can define some equilibrium concentrations, right? So if that's equal to 0, then clearly we can say that these two terms are equal, right? So let's just copy that out. Let's take this across to the other side. Right, so that's what we have at equilibrium. And now we can see we can rewrite this, even though this is the equilibrium amount, this is the concentration of A in the reactor still. And we know we can rewrite that in terms of conversion. So this is CA naught and then 1 minus XA, and we'll say E. So this is the conversion at equilibrium. Now B is the product, right? And just remember, B is the product here. So you've often seen B as another reactant. Here there's no other reactant, B is the product. So B is the product, so CBE is so B is produced from A. So we can say the amount of B that gets produced is the amount of A that's been converted. And we are looking at the equilibrium condition here. So this is XAE, right? So this is the condition that applies at equilibrium. And we can see in this equation, we can cancel the CA naughts. And the next thing we'll do is group out for XAE. But the other thing I want to do is just divide through by KR. So KF over KR. Let's take this one out here. And then we can group the XAEs. So the XAE here, this is in effect times 1. And then we're going to bring this across here. So this is going to be plus KF over KR. And so we've gotten rid of this term. And so then we have just left over 1 times this, which is that, right? And so we can say here XAE equals this thing divided by this thing. Okay, so this now gives us a nice relationship between conversion and temperature, right? Because both these are Arrhenius expressions, right? You've got an Arrhenius expression for the forward and the reverse. And so on both sides, you have a temperature function. So I just want to replace this by KE, the equilibrium constant. And this one, and it's the same for this one, right? Okay, and so this function has an exponential dependence on temperature, and this is the conversion. And if you were to plot this out, you'll get a line that looks a bit like this. Let's do this here. So if you were to plot, and I'm actually going to do this temperature conversion, temperature and conversion, and you'll get a line that you'll see often looks like this, right? So if you were to plot this out and actually do it as an exercise, you'll find lots of examples in the notes where you've got constants given, you've got the Arrhenius constants given, and then you can just apply different temperatures and calculate that and then generate the curve. There's a question here. Would that mean net conversion is constant? So let's think about this question. So I guess, Jonathan, you're talking about, I guess, around here, right? So, yeah, so you are saying, if we are saying dc dt equals 0, and we've got this conversion defined, that it's a constant. So yes, that's correct. It is a constant. In fact, the fact that this is 0 is the definition of this value of conversion. And remember, this is a specific value of conversion. It's the value where the net rate is 0. Another way to think about this is, let's imagine what happens if you take a batch reactor. So let's draw a batch reactor here. And let's imagine what happens over time. So let's say we start out with component B, component A. So you've got component A in this reactor. And then so initially we have this situation. We have component A in the reactor at a certain high concentration. And then as time goes on, A gets converted to B. So this one disappears, and we've got B instead. So A is converted to B. So the conversion of the concentration of A will start to go down, and the concentration of B will start to go up. And there will come a time where these two will no longer be changing, right? So you'll reach a stage where your concentration of A and your concentration of B are such that the rate of conversion from the one to the other, so the conversion of A to B, becomes balanced by the conversion from B to A, right? So these two rates become equal. You see, initially, these rates are not equal. Initially, you have so much A that you've got a much higher conversion of A to B. It's something like this initially. Oops. It's something like this here. And then for B, it's something like this. So initially, there's an imbalance. Initially, you've got a far greater conversion of A to B than of B to A. But as time goes on and the amounts change, you reach a stage where the rate of the two reactions become equal. So that's equilibrium, right? Does that cover your question there, Jonathan? Okay, thanks. All right, so that's true. Your conversion, and in fact, let's take that a bit further. Your conversion, it is true that the concentrations were changing over time, so they become constant at equilibrium. And this is all specific to a specific and particular. So this is all specific to a temperature T. So all this is happening at some temperature, let's say 300 Kelvin. And of course, we may have to do some extra work to keep this at 300 Kelvin. It might be that we have to add heating or cooling to maintain the temperature at 300 Kelvin. Now, if we change our control, let's say we had controllers with heating coils and cooling jackets, and we force the system to stay at 300 Kelvin, then all this would happen and we'll reach a certain equilibrium. Now, from the relationship that we've got here, it turns out that the conversion is a function of temperature. So if now we change our set point on our controller and say, well, now I want to operate at 350 Kelvin, you'll find now that we are no longer at equilibrium, that there's a different set of values for A and B. And in fact, let's move this. How do we, does it have, okay, here we have a freeform selector. So let's move this. So we initially settle down to a certain equilibrium at 300 Kelvin. And so let's indicate that we're operating here at 300 Kelvin. Oops. So this is 300 Kelvin. And now we're going to change our temperature and we're making it, let's say 400 Kelvin. So we push up to 400 Kelvin here. And now suddenly we are no longer at equilibrium. And what this means is in nature has a certain balance between A and B at 300 Kelvin. At 400 Kelvin, we are not at that same balance. And our system is going to then shift. And it might do something like this, let's say. And the other one will do this. And now it's settled down to a different equilibrium, right? So it will take a bit of time, but you'll reach a different equilibrium for this different temperature. So this is what we are writing here, that for a given temperature, there is a given equilibrium, and then that equilibrium will change. So as we change the temperature, the position of that equilibrium also changes, okay? Any questions or comments on that? Okay, now going back to this picture. So if we plot out the change of that equilibrium, right? So this is X equilibrium. Then we can see it will have roughly this shape. And I was saying earlier, please do go ahead and plot some examples. Take some examples in the notes. The constants are given. Go ahead and plot for different temperatures. Look at how your equilibrium curve looks. And so you'll see that it has this shape quite often. So for exothermic reactions, you'll see it has this kind of shape. For endothermic reactions, you'll see the shape is the other way around. It's more like this, right? So, so that's your equilibrium condition. Now that's different to our energy balance, right? Remember the energy balance, we said here, this was our energy balance. So these two lines, we said for the exothermic case, as temperature rises, or rather as conversion rises, more energy is given off, more heat is given off. So it goes up like that. And we know also that we are entering this reactor, or we are starting this reactor from a conversion of 0. So we are starting down here somewhere. And if it's exothermic, then it's going to rise like this, right? So this is our reactor chugging along, right? This is a hypothetical nature. I'm not sure if you can see my cursor. It's pretty fine over here. But I'm pointing here along this curve, the equilibrium curve. So you can see nature says when nature is at rest, when the net reaction rate is 0, then nature sits on this line, right? This is where you'll find nature sitting, right? When we are at rest, this is the state of nature. But our reactor is not sitting at a state of rest. Our reactor is it started out here, right? It started here. And in fact, we can refer to this, to what we drew over here. We said the conversion was 0 initially, and then the conversion was rising as time passed. And as time passes, and now let's say we are not controlling the temperature in the reactor, right? So earlier when we were just trying to understand the relationship between conversion and temperature, when we were trying to understand this equilibrium line, we were thinking about fixing the temperature in this reactor. Now, let's say we didn't fix the temperature. Let's say we weren't, we are now switching attention back to non-equilibrium. And we are saying, let's say we start here and we just let the reactor react. So the conversion will rise and the temperature will rise if it's an exothermic reaction, and it's going to do this. And it's pointing towards equilibrium. Is there any reason for that? Right, and you could say, well, is that just a coincidence, right? Let's draw the other case. So if you have, show why I'm getting it wrong. Yeah, so let's say you have the endothermic case. So the endothermic case, it turns out if you plot that equilibrium curve, it actually looks like this. And in this case, from what we said earlier, as the conversion rises, the temperature drops. So in this case, it looks like this. So you can see here that our system is again pointing at equilibrium, right? So in the endothermic case, we are moving up like this, pointing at the equilibrium curve. In the exothermic case, we are again pointing up at equilibrium, right? Any reasons for that? Right, so it's because, as you'll often hear, nature always moves to a state of rest, right? Your system will move to the state of stability, right? This is actually not generally true. It's not always true that everything in nature goes to a state of rest. But if a rest state is available, if there's a stable rest state available, then nature will tend to find its way there. So you find that you're moving towards equilibrium. And you know the Le Chatelier's principle. So this is, if you like, the advanced level of Le Chatelier, that you are starting away from equilibrium and your system is moving towards that equilibrium, right? So this is your energy balance pushing up on the straight line here, and this is your equilibrium balance that we derived earlier. So with those two, we are starting to see a plane here. And you see, on this side of the plane, we are starting from the state where, on balance, we are consuming component A. So down here is the desirable region, right? All along here, we have component A being consumed. Above the line, we have component A being produced. So we can think of this as this region is not so interesting to us because we don't want to produce component A. We want to produce component B, that's the product. So we don't want to operate up here. Down here, we are producing valuable products, so that's where we want to be. So we have started down here, and now we've said that we are moving up along this line. Now we have to decide where we are going to go along this line, right? Because you see, it never really ends, right? You see, you can say, well, doesn't it end on here? Why don't we just go here? Well, remember, as you get closer to equilibrium, your driving force is going down, right? As you get to this region here, where your two rates are equal, you've got a net zero rate here. And you can stay on this net zero rate for any period of time, right? How do you decide how long to go for? And it's also the case that we are not really productive here. So we don't want to be near this highly, near the state where nothing on balance is happening. we want to stop somewhere short of that. So we want to pick a point that's just short of that equilibrium, or we don't know if it's just short or if it's far short or what, right? So we want to know how far. We know we are starting here, and that reactor is going to chug along until it gets to some point. Now, our design, right, the whole point of thinking about this is we want to know, where do we stop on this line? We know we are moving along this line, but where must we stop on this line? And when I say we are moving along this line, let's think about the 3 reactor types, right? For a CSTR, we can move along that line simply by creating different sizes of the CSTR, right? So the bigger you make the CSTR, the greater will be the space-time and the greater will be the conversion. So as you make the CSTR bigger and bigger, it moves up this line. Now, if you take a low value here, you'll get a nice small CSTR. If you take a point with double the X value, you'll get a volume that is more than double, right? So for a doubling in conversion, you don't get a linear increase in conversion, right? And if you, let's say 5 times that was somewhere right here, you see right here, even though you have 5 times the conversion, this might be 1,000 times the volume or 10,000 times the volume. That's because here the rate is so low that you need a crazy volume to achieve any kind of conversion. So that's where you would go back to the balance and think about, as we did quite a bit already, how the volume requirement of the CSTR increases as you get closer to equilibrium. So you see, moving along this line is not an easy thing, right? We can't just say, okay, I want double the conversion, so double the volume here. It doesn't work linearly like that, right? This is, although this line is straight, hidden behind it is the reaction rate, which we can't really see as yet, right? So let's think about a way to view the reaction rate on this plane as well. So we go back here, right? So far, this approach has given us this interesting line, this equilibrium line. So let's go back here and say, well, let's not go all the way to equilibrium now, right? I know where equilibrium is, so I know equilibrium is all along this line. What about other rates in between? So let's take this equation, so this one, and say, okay, I don't want equilibrium now. I just want to know what's the net rate here. So not equilibrium anymore, but now I want to define a certain net rate. So let's call that RA net. Okay. Now this RA net, the same, and we are not at equilibrium anymore either, right? So now we are saying we are interested in some non-zero reaction rate, and then to get that, we're just going to do the expansion as we did before. So we'll write this as CA naught 1 minus XA, and this will be CA naught times XA. Right, so that's the balance we have now, and that's all equal to this RA net. And we can do the same as before, and we can group out for XA, and so we can rewrite this as, let's take this term across here, so we can say plus this thing on this side. That's plus. So we can forget about this 1. And now we've got XA, and we can group out the XAs here. And we can group out CA naught. So we can say XA CA naught equals this stuff. Right, and now you see the CA naught can cancel, but we didn't write it there, so let's just keep it. So we can rewrite this as, let's just divide the left-hand side by this. And then divide by CA naught. Right, and this is now another equation that we have available to us. And what we can do here is fix the rate of interest. So we can say, I want to know what curve I would get between x, a, and t. Remember, the other variable that's hidden here is t. And so all these k's are t functions. And so all I need to do is fix a value for Ra, and then that will define a relationship between xa and t. And that's how we generate the so-called isorate lines. So, okay, let's draw a new one. So we've got x and t. And for an exothermic reaction, we've got the equilibrium line here. And then if we set a low value for Ra net, so in fact, this equation you can think of as a generalization of the equilibrium equation, because if you just set Ra net to 0, then you get your equilibrium equation. Now let's set a small value for Ra net. So if we set a small value, then that's going to get us close to the equilibrium line. So that's going to define a line that looks like that. And then if we take progressively smaller Ra net, progressively bigger Ra net values, so we slowly increase Ra net, then that will define yet more lines for us. So there might be another line here, and so on. In fact, what actually happens is you find that the peak shifts around. And again, do this as an exercise. Be sure that you know how to draw these these isorate lines. So in effect, we have the equilibrium line here, Ra equals 0, Ra net equals 0. And then this might be 1, this might be 10, this might be 50, and so on. Right, so we now have quite a lot of information on one set of axes, and part of the challenge in this section is just keeping track of all the variables in our head, right? So you've got conversion, you've got temperature, and you've got reaction rate. So reaction rate, remember, is we choose a value according to which curve we pick here. So when we talk about an Ra net value of, let's say, 5, right? Remember, 5, it's between 0 and between 1 and 10. And so that might define a line here. So you have to kind of approximate a 5 line here. So we can say Ra is 5 here. So we set Ra net equals 5, and then we solve that equation and we draw a curve here. And then you can ask questions like, at 400 Kelvin, at a rate of 5, what's the conversion in the reactor? So that would define that, right? So that's that bit of information. Now, the reason we'll be using this plane quite a lot is because it summarizes nicely everything that's going to happen in our reactor. And I actually want to pull up a slightly more, a slightly better organized diagram of this. So I'm just stealing from the tutorial. So let's go to my development folder. So let's take this one. So if you look in the tutorial, you'll find that this is this cut off. Let's see if I can rotate this here. So you'll find the numbers given that are used to generate this figure in the tutorial. So be sure that you are able to generate this. And now, of course, this is the equilibrium line here. So this is the region that we want to avoid. And in this problem, so let's look at this, this question in the tutorial. In this question, we are told that we have a CSTR in series with a PFR and so on. And we are entering the reactor. A fresh feed enters with a temperature of 300 Kelvin. Right, so we are entering the reactor at 300 Kelvin. So here's 300 down here. And if it's the feed stream, then conversion is 0, right? So you've got conversion here, and here's temperature. And we are given that we are entering at 300 Kelvin, right? So that defines our starting point to the reactor. Right, the next thing we have to do is figure out how far we want to go along the operating line. Now, to draw the operating line, you'll see that this is the equation. So going back to your energy balance that we showed earlier, if you don't have heat added to the system, then this equation applies. Remember, when you do add heat to the system, then you've got plus Q and you've got UA delta T and so on. But if you don't add heat to the reactor itself, then this is the equation that applies. And the reason we can talk about not adding heat to the reactor is because you see in the way this problem is defined, you've got a cooler between the units. So we are not adding heat directly to the reactor. We are adding heat or removing heat between the two reactors. So if that's the case, then there's no heat is being added to the system. And we can treat this as the adiabatic equation. So we know this is the right equation to use for our line. If we look at this line also, if we look at the equation for this line, all the heat capacities are positive. Beta is positive, right? Inlet feed ratio, not stoichiometric coefficient, inlet feed ratio, that's also always positive. And then you've got heat of reaction, minus heat of reaction here. Now, for an exothermic reaction, which if you follow this question, you'll see it is. So this is an exothermic reaction. That means delta heat of reaction is a negative number. So minus a negative number, that's a positive. So all the stuff up here is positive. And you've got X and you've got T there. That means dx dt is positive. So the slope of this line is positive. So we know that we are going to be moving in a positive slope like this. So this is what the operating line looks like, right? And as we said before, we are trying to decide now how far along this line we want to go. So this is the constraint right here, right? This point is our equilibrium, right? Earlier, I didn't draw this line very well. I was trying to draw along this equilibrium line, but that's equilibrium. That's the point we don't want to be at. We do want to progress up this line. We do want something to react in our CSTR. We don't want to get all the way there, right? So that's what we are trying to figure out here. Is this all clear? Any questions or comments there? Right, now we want to know how far to get along these along this line. Now, one thing we can think about creating for ourselves is a so-called maximum rate path. So in other words, if we are at a certain conversion, so let's say we are currently at conversion 0.3, however we got there, we've got some reactor, we have gotten ourselves to 0.3 conversion. And we are talking all CSTR, right? So we've gotten, not that it applies and blah, 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 you know all that, all this is generally true, but for now, for this problem we are talking about a CSTR. So we got to 0.3, and we want to know where's the best place to be on, if we think about it in this reactor, what temperature would give me the maximum possible rate, right? We know there's some temperature that applies in here, but if we were able to choose that temperature, which one would it be? And we can answer that question just by looking horizontally here. So we can say, given 0.3, we just need to look along this line and look for the highest rate. And of course, this is 0 rate, so that's the worst possible rate. This is close to 0, so this is a lower rate also. But now we are getting to the higher rates. So now we are seeing, as we move along this line, we are getting closer and closer to a higher rate. And now you can see here, okay, this teal line is a higher rate than for the red line. But as we move closer, we are getting closer to this, this line, which is an even higher rate. And you can see the numbers here also. You can see as we are moving horizontally, we are going from 10 to the minus 5, or 10 to the minus 6. Sorry, you can't see this so well. But that's 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. So we are getting closer to 10 to the minus 2. We can see we can never reach 10 to the minus 2 moving along this line, because that curve seems to be rolling down there. So we won't get there, but we can try and get as close as possible. So, but then of course, you see, you start to intersect with the other lines, right? If you go out of this again, then you're going closer to equilibrium again. So it's not that we are just going as far horizontally as we can, but there exists a point, and it's going to be somewhere around here, right? There exists a point somewhere in this region where we've got the maximum rate. And we can do that for all conversions. We can pick a different conversion, let's say here. We can draw a horizontal line, and we can see the maximum rate is somewhere in this region, right? And the thing is, for us as a CSTR, right, we are moving along this line, right? According to our reactor, we can only move along this line. Right, so now the question becomes, along this line, right? Along this, I want to say a color. So along this black line, right? That's the only unique color now. Along this black line, what's the best possible? What's the best place to stop? So maybe I'm not sure how you're going to answer me. So maybe I'll draw a couple of circles. So stop me when I'm at the right place. So is it this point? No takers. This point? No takers. This point? No. This point? No. This point? You guys are oh, there we go. I was going to say you guys are disappointing me, but thanks, Jonathan. Zuhaira, yeah. So yes, you can see that when you get to this point, where's this cursor? Okay, so when you get to this point, you are now closest to this teal line. When you move away from this point, when you go past this point, you are going closer to the red line again. So your rate is going down as you move away from this point. And then before you reach this point, your rate was again closer to the red line. So you see there's a maximum point to find here, right? So near this point, let's make this, so near this point, we seem to have a maximum, right? Because as you go past this point, so along this line, as you go past this point, when you consider points here and here, you are going closer to the red line again. That's a lower rate than the teal line, right? At this point, you are on the teal line. as you go below, then you are going away from the teal line and you are going closer to the red line again. Now, in what I'm saying here, all of it is basically that the tangency is the best point, right? So if you think about it, we are saying that the best place for our operating line to stop is on the point of tangency with the teal line. And then we can repeat that. We can say, okay, if I took that same line and if I considered starting at a different temperature, then I'll get a point of tangency here. So at this point, if I go past this, I'll be getting closer to the green line, which has a lower rate. Below this point, I'll again be getting closer to the green line, which is again a lower rate. So this is another good point. And we could repeat that here. So consider a different inlet temperature for the same reactor with the same slope. Then that's the best point. And then up here, that's the best point. And so you see, we've got a set of points now that show us where the best rate is. So we can go ahead and connect these points together. So we can draw a line here. And so that is what we call the maximum rate line. Noting that this maximum rate line is specific to the slope, right? So for this slope, we have this, this particular green line, right? If the slope was different, then the point of tangency will be different, right? If the slope was like this, then the point of tangency would be here and here and here and so on. So this line, the so-called maximum rate path line, is specific to the slope. And then we have to go back and think about what that slope means. So let's look at our balance again, right? So this is the slope. And you can see this slope, fine heat of reaction, we don't think we can change that much. But you see this value theta, that's our inlet flow ratio. That's totally up to us. We can choose the ratio among the species coming into the reactor. So we are fully in control of the slope of this line. So this is another design decision. We have to decide what slope of line we want, because that's going to move our maximum rate path. But for now, for simplicity, let's say that was fixed, right? So we were given a problem where we were told our inlet flow ratios are these values. And so that defines our slope for us. So now we've got this maximum rate line. Now we want to think about for the CSTR, what do we do with that line? For the PFR, what do we do with that? For the batch reactor, what do we do with that? Right, so we've got the three main reactor types, the three ideal reactor types. And by the way, later in this course, we'll go to other reactor types. We'll generalize among all of them. But for now, oops, batch reactor, right? No flow. So we've got CSTR, PFR, and batch. So we've got some interesting lines now. We've got equilibrium. We know that's a no-no. We don't want to go near equilibrium. We've got maximum rate. That's looking good. It looks like we get a good rate, but we stay away from equilibrium. And we've got the starting point. So those are some promising lines to work with. And then it's tempting to say, well, then why don't we just react up to the maximum rate path, and then that defines where we'll stop. So we can start thinking that way. So for the CSTR, we can say, okay, we'll do that. We'll start here, and I've made a nice mess. So I'm just going to draw a little offset from here. So let's say we started there. Then we say, okay, I reach my maximum rate path. So that tells me this is my CSTR. In other words, this is my operating point for my reactor. In other words, I can read off this point. It's about 348, maybe 348 Kelvin, and conversion of 0.3. So that tells me I have a CSTR that looks like that, right? So there's my CSTR. But if you look at the problem is saying we want to achieve, okay, I don't want to read the whole thing. Let's say the problem was saying we want to achieve 0.7. So we want to get all the way up there. Now, clearly, although this is a nice design, this is making good use of the space. It's never going to get us to 0.7. There's no way without, even if we violated maximum rate, even if we ignored the maximum rate path and just kept going further and further, then we still can't get to 0.7 because it's past equilibrium. We can never make such a big reactor that gets us there. So what can we do? So we can think about, of course, then having a second reactor, right? And that's a solution that we saw in the first part when we wanted to achieve small volumes and good conversions. We used 2 CSTRs in series. So let's think about a second CSTR, but adding a second CSTR on this line is only going to get us further along, which is inefficient. So what we want to do now is cool down the mixture. We want to pull ourselves back here. So we pull ourselves back, and then we allow ourselves to react up again, right? So in terms of our drawing, we add a cooling thing here. So we add not a cooling thing, a heat exchanger, and we now add another CSTR, right? So there's a CSTR. So that's a second reactor we have in the series. Now we have to think about how much cooling we want to do here, right? How big of a heat exchanger do we want to create? Because the more cooling we do, the further back along this line it's going to get us, right? So for now, let's just say we will cool back to 250, which is very expensive, by the way, because it means the moment you go below 300 Kelvin, you have to use refrigerants, right? Remember, 300 Kelvin is approximately ambient temperature. So you, to go below ambient temperature, to go below 25 degrees Celsius, you need to use refrigeration and so on. So, so we would normally not want to do that. But anyway, for now, let's just say we go ahead and put in ammonia plants and all of that and do cooling, right? That's what you have to do in industry when you want to cool below ambient, right? It normally means adding ammonia plants. You have to add a whole other plant. So anyway, we've done that, and now we are able to cool down to 250, and now we've got our second CSTR, and now we can think about again going up along this line, and we could say, well, we'll stop there, and then we can cool again, and actually it looks like we need to go back even further if we want to have any shot at reaching the 0.7. So that's one option. The other option is to say, well, I don't want 3 CSTRs. Every time I add another CSTR, that adds a lot of cost to my system. So instead of going and adding another cooler and another CSTR, I'm just going to not operate at maximum. I'll let my second CSTR be inefficient, and I'll get it there. I would say this point is a bit too close to equilibrium to try and do that. So either you want to pull this temperature back, or get here and then put it back to a smaller degree and then do that. And you see, these are all design choices. So in terms of a design, now there's a lot more free play. And notice here that at this point in your whole chemical engineering curriculum, you are switching to this mode, right? Up to now, it's been, here's a problem, here's the equation, you can solve it, there's the answer. Now it's more like, what do you want to do, right? You can choose your answer. So there's a lot more free play in the problems you'll be finding now. So you've got free play in terms of how far back you want to cool this first reactor, how far back to cool the second reactor, whether or not to have a third reactor or just violate and use a second reactor. So that's what you can decide. So and there is a nice criterion we'll work out to answer that. But before that, you'll notice here, or you should be feeling uncomfortable about something. which is, why are we saying this line must be parallel to this line? To this line. So this first line we understand, right? This first operating line, it's written in terms of the inlet molar flow ratio and so on. Why are we saying this line is also parallel to this line? Because remember, our inlet flow ratio to the second reactor, those inlet flow ratios are not the same as for the first reactor. What's the reason we can do that? Any takers there? Right, so the reason is that we are drawing our bounding boxes, right? Our first energy balance was written across this bounding box. Our second energy balance is written across this bounding box, right? It's not written across this, it's not written across this individual reactor. So when we do our energy balance, we are always referring our balance to the entry flow rate here. And you'll say, well, then aren't you artificially, your heat, isn't that violated here? Well, you draw these arrows crossing the boundary. So you still have to add heat for this heat exchanger. But the way you do that is you say, well, my first reactor goes up here. Then when I'm drawing my second balance, to keep the energy balance valid, I will shift myself along here. Now I know I've accounted for the temperature change from this part. And now I'm still referred to the entry point, right? My bounding box is still across that entry point. And so my slope is still the same as for the first reactor, right? That keeps this graphical approach rational, because otherwise we would have to find a second maximum rate line, right? This green line, we would have to find another maximum rate line, and it gets really messy. But anyway, if we keep referring to this entry line here, then we can keep these operating lines parallel. And so I just want to point, yeah, so we can keep this operating line parallel to this operating line, and we can progress that way. Any questions or comments there? Okay, so now we want to figure out a criterion. We don't like to have so much free play. It is inherently like that. Maybe to say, in design problems, the way to figure out, the way to reduce your variables, the way to get a good design is to reduce it to a single simple criterion. And the simple criterion in making these decisions is unfortunately a kind of vulgar answer. The answer is money, right? You look at the cost of your process. So if you choose a value somewhere around here, how does that change your cost? When you choose a value here, when you think about adding a third reactor or violating the second reactor's efficiency, how does that change the economics of the process? And that's a fairly long-winded calculation. It goes to the profitability of the whole process. You have to look at the capital costs and the operating costs. The fact that as you add more CSTRs, you will be increasing the utility use and all those kinds of things. And you'll do quite a lot of that in the fourth year. In the third year, we simplify some of those costing approaches, but that's how you can answer it. You can say, well, these are just design variables. I don't have to, there isn't going to be a nice equation that I can just solve to get this, but what I can do is just let these be variables and just let this vary in this way, let this vary in this way. So let everything vary and just look at the money and see where's the profit the highest, and then take that as my solution. So that's how you solve multi-dimensional problems. You just search for, you just create an overarching criterion like the net profit for the process, and you look for the best profit in there. So that's one way. We are still in third year in this course, so we can still be kind of dewy-eyed and how to say, highly principled. So taking a highly principled look at this, so not worried about money. We are looking at just the principles of chemical engineering. So we would say, well, then I always operate at the maximum rate. So I'm going to stay here. And then here I'm going to cool back to this temperature, and that will be my maximum rate there. And then that means to get to 0.7, I need to cool back here. So you could start from here and say, what do I need to cool back to get to this point? So you can start from your solution. Maybe you set a constraint. So maybe as a constraint, we say, don't ever go beyond 220. Don't ever go below 220. So you say, okay, 0.7 is here. Here's my maximum rate line that defines this point. Choose a different color. That defines this point. So then I can solve backwards till I reach 220. Okay, so that's there. Then let's go back to the maximum rate line that defines my other reactor. Then let's cool back to 220 again. That defines this point. And then that defines here. Then that says I'm allowed to start as high as this temperature. So for the CSTR, yes, operating at the maximum possible reaction rate using this green line, that's a useful way to do it. Okay. Okay. Now, is the situation the same for the PFR? Would you stop at the maximum rate line if you had a PFR? So I'll give you a couple of minutes to think about that. You've got a PFR. So you enter your PFR here. Let's use a different. So you enter your PFR here. And as you look at different points down that PFR, so you are making longer and a longer and longer PFR. So as you make this PFR longer, you are getting to different conversions. So how long must this PFR be, right? You could stop on the maximum rate path here. Do you want to stop on that point? Any takers? Okay, no one's feeling brave yet. So you shouldn't stop on this point, right? Because why would you abandon this PFR just when things are getting good, right? So your reaction rate is low down here. It's increasing, it's improving. Your reaction rate is getting better. So your reaction rate is rising. Now, why would you jump out just at this point when things are getting good? So fine, it's reached its maximum. I shouldn't have drawn it that way. It's more like this. So it's reached its maximum point here. The rate is still good here. So you might as well keep going for some distance further. And then of course the rate gets really bad at some stage. So you should jump off somewhere here. So we don't know yet where. But we can say, well, what we want is not a single PFR. We want a train of PFRs that's going to get us to 0.7. So what we want to do, what we need to do is think about the train of PFRs, not a single PFR. We want our train of PFRs to closely follow this maximum rate path, right? So it's not that a single PFR should be optimized, it's the whole train. And the best way to create this train of PFRs is to dance around this green line. So we want to create our PFRs so that we are zigzagging around that green line, right? And because think of the alternative. Let's say we did this. I'm doing all that. So let's say we started here. Where's this thing? Okay, we started here. And now let's say we did this. We went up to the maximum rate line, we stopped, and then we cooled, and then we went back to the maximum, we cooled, and we went. If we did that, then you see we would be jumping off just when the rate was getting high, then we'd be cooling out, and then we'd be pushing ourselves back to a lower reaction rate region, and then we'd be pushing ourselves back up to the maximum rate. So it doesn't really make sense to do that. So what we would want to do instead is react past the maximum rate line. Then when we cross here, you see we are still staying in a relatively high rate region, so that when we go up here, then we cross again and we still stay in that nice high rate region. So we try and trace the path of the maximum rate. And that way we navigate our way to the a nice conversion. Right, so that's what we can do for the PFR. Then the question becomes then, how far do you take that? How far along this line do you go before you stop, right? And for that, we don't have a nice, elegant answer. We have an answer based on an observation that has worked fairly well in chemical engineering. So the 10 degrees to equilibrium line. So we look at equilibrium and we just think of a suitable margin. So we say, well, if I look at where equilibrium is, I am pointing at this equilibrium. I know I can never reach it, but the longer, if I make my PFR infinitely long, it's tending towards this point. Now, I don't want to go, I'm not trying to go there, but I can figure out what that temperature is. So if I make my PFR infinitely long, then I'll maybe have a 402 Kelvin. So let me just subtract 10 from that. So 392. And I'm going to stop there. So that's the approach that's often taken in chemical engineering. We take 10 degrees short of equilibrium. And so again, we can create another line. So we take lines parallel to our operating line, and we look down by 10 degrees. So here's 10 degrees, here's 10 degrees. And so we use the equilibrium line and the slope, and we produce for ourselves the 10 degrees to equilibrium line. So let's say it's like that. So for the PFR then, we can shoot up to 10 degrees. Then we say, well, the other thing is I want to stay close to my maximum rate path line. So I cool across here. And here, again, we have to think of a criterion for how far to cool down. And we could also just say, well, there's a certain constraint. I don't want to go below a certain temperature. But in principle, we are trying to straddle the maximum rate path line, right? This green line here, that's still our maximum rate path line, right? Remember that that's a function of our slope. So the slope is the same. Our inlet flow ratio here is the same. So our slope is the same, even though it's a PFR. And so I decide on an end temperature here, and then I go up again. I reach my 10K to equilibrium line, cool down again, up again, until I reach my criterion. So I can stop here. Right, so that's what you would do for the PFR. You wouldn't stop on maximum rate. You would go past. You still avoid equilibrium by staying this arbitrary 10 degrees short of it. And actually today the computing is fast enough that you can compute this quite much more accurately. Now you can search the whole space using the economics, and you can really get a highly optimized design. For this course, it's enough to use 10 degrees to equilibrium. The other thing is, the other variable to optimize is how far back to cool. And in this course, it's kind of okay to just say, well, approximately the same distance across the maximum rate path. So if this is 50 Kelvin, then just take 50 Kelvin before that. But know that this is a very arbitrary way to say that. More correctly, we need to add in the economics and figure out the actual costs of cooling so far back and all those things. Right, so that basically covers it. Two different ways of navigating this plane, right? That's the way to think of it. That there's this plane that nature defines. So nature defines the reaction rate will become this if the conversion is that and the temperature is that. So nature has set this plane, right? You can imagine the curves, the iso rate curves. That's all nature. And we are coming along with our little lines and our little reactors and just trying to find our way through the storm of nature here. And so we are, these are some of the principles we use. So we want to stay far away from equilibrium. There exists a maximum rate, and we try and stay close to the maximum rate line. So based on those few principles, we navigate the plane and come up with a sensible design. Any questions or comments there? How would we limit the conversion to 0.3 in the first reactor to continue in the second reactor to some greater conversion? So how would we limit the conversion? So I guess you might be thinking, well, why would we say we are going to limit ourselves to 0.3? Right, because if we leave, let's say it's a batch reactor, and we leave it running long enough, then it is just going to keep on going and slowly reach a steady state here, right? That's a steady state line also. I should be pointing here. So, so how would we limit it to stop here on the maximum rate line in the case of a CSTR? Well, remember, it's not the case that, or let's say it is the case. Let's say it is in a batch reactor. Well, we can simply stop the reaction there, right? The batch reactor, remember, we can depressurize it and extract our reactant contents from that batch reactor. So we do know when we will reach there, right? Because we have the kinetics, we have our mass balance. We can write dx dt equals minus RA over FA naught or over NA naught. So we can solve that balance and say, okay, if we start at this ratio and this temperature and we let it react, it's going to reach this point in, I don't know, 42 minutes. So at 42 minutes, we depressurize and we remove the product from the reactor. So that's what you would do in the case of the batch reactor. In the case of the CSTR, you would simply design this reactor such that your space-time did effectively that. You would figure out, okay, this whole reactor is going to operate on this point, and I know I reach this point if my volume is, I don't know, 63 cubic meters. So you work out the volume, right? Remember, in the first part of the course, when we defined a conversion, we could then calculate a volume. So we calculate a volume. In effect, we are calculating a space-time. We are choosing a volume that's going to result in a certain average residence time in this reactor, and that means that continuously we will have only a 0.3 conversion in this first reactor. And then similarly, in a plug flow reactor, we make it long enough, we make it just long enough to reach that 0.3. We know if we make it longer, well, in the case of the PFR, we do make it longer, but let's say that was 0.4. So we make it just long enough for 0.4 and no longer, and then we know it's going to come out at 0.4 there. So yeah, by controlling the volume of the space or controlling the time of the reaction, we are able to choose these endpoints. Does that answer it there, Jonathan? Thanks. Okay, so that's how we design these reactors. Let's think about the batch case. It's actually not the same in the batch case. I need to copy this to a new thing. Right, so the last one quickly for the batch reactor. Okay, for the batch reactor, you see, we have a few more options available to us. So in the batch reactor, we can think about the fact that we can actually continuously control the temperature. So in the batch reactor, we can add a heating coil, and we can add a cooling jacket. So we can fit this reactor with all the temperature control that we can actually control the trajectory of temperature over time. So think about this. Your reactor is tending to change in its temperature, and then we go along and blast it with some cooling water and push it down here. And then we want it to go to a different temperature. So we blast in some steam and then that pushes it up there. So you can think of in the time sense, if we think about applying control, and in fourth year, we'll look at how to design these controllers. You can design a controller to control that temperature as you like. So we have a lot more freedom in this batch case. In fact, that's one of the reasons to go batch. There are disadvantages if we are doing commodities chemicals, but for fine chemicals, because we can do such fine control of the reactor, that's a big feature. So for pharmaceuticals, you do quite a lot of this. So anyway, you can control the temperature quite explicitly in the batch case. And of course, your conversion is going to respond to that. So as your temperature changes there, through your material balance, your conversion is also going to just it won't go down. Your conversion will also be changing in some way. So what that means is we can choose how to control the temperature on this batch reactor. And we can actually try and stay on the maximum rate path. So even though it's true that we can really control the temperature in any explicit way, still there does exist a maximum rate path. So given any conversion, so if you pick 0.2, there does exist a maximum reaction rate along this horizontal line. Given 0.3, you can find a maximum reaction rate. So the same, but it's different in the sense that it's not anymore based on the inlet flow ratio. It's now based on, you can simply look left and right on this among these curves and look for the maximum rate. In fact, here it would be this point. So this green line is not drawn quite correctly. For the batch case. So for the batch case, you've got a certain line which you can find just by looking up the maximum point. In fact, the way to do it then would be to take the maximum points on these isorate lines. That would define, that's where your tangency in this case is the horizontal line. So this is your maximum rate path in the case of the batch reactor. And you can actually derive an equation for that. If you look in the notes, we did that there. So we've got a maximum rate line here. And once more, just carefully be sure you understand why we take the maximum point there. So if you pick a certain conversion, there does exist a maximum reaction rate. So, and you can see if you pick this point, all points to the right are closer to the red line, all points to the left are closer to the red line. So this must be the maximum rate. Over here, all points to the right are closer to the green line, all points to the left are closer to the green line, which is a lower rate. So that is the maximum rate, that's the maximum rate. So that's the locus of maximum rates. So that's a maximum rate line. And because we can apply such fine control to the temperature, right, even though we are starting, let's say here, right, let's say we do nothing for a while. So let's say we just let the reaction proceed. So the reaction will proceed adiabatically. So when we say just let it proceed, that means we don't try and apply heat and cool. So we let it go adiabatically. So it will adiabatically go according to the adiabat that we defined before, right? So according to this equation here. And this ratio will be your initial molar ratio. So your ratio of your species in the reactor initially. So it will go up like that. And then when it reaches the maximum rate line, what we can think of doing is cooling this reactor such that we stay on this maximum rate line. So we look at this rate line and we say, in 20 minutes, the conversion is going to go up to 0.4. if I look on this graph, I want to reach 0.4 at a temperature of 360 Kelvin. My current temperature is 390 Kelvin. So I know over 40 minutes, I must reduce my temperature to reach 360 Kelvin. And you can keep doing that. So you can, in the case of the batch reactor, stay identically on this maximum rate line. And you know then that you will reach your target conversion, 0.7, in the minimum possible time, right? In the case of the batch reactor, that is the variable you are trying to reduce. You're not trying to really reduce volume anymore. You're trying to reduce the time taken to reach the desired conversion. Right, so you get on the maximum rate line and you use temperature control to stay there. If you're wondering how can we talk about using temperature control, think about this. Think about, say currently you are at a conversion of 0.45, so here. So currently your reactor is there, and we're not specifying what temperature, we are just saying your conversion is 0.45. And then you can say, okay, if I'm here, then I'm going to blast in as much steam into my heating coil until I quickly get onto here. During that time, your conversion may go up slightly, so you try and meet that line there. On the other hand, if you are down here, then you'll say, let's dump as much cooling water or refrigerant in until I reach that maximum rate line. And you can keep doing this. So at each instance, you can say, oh, am I above or below my maximum rate line temperature? And then add heating or cooling until you stay there. So you can use temperature control to stay on this. And I wrote a nice simulation that actually tries to do this. And it works. It stays on the maximum rate line, and you can and you can get the minimum possible time in that batch reactor. So that's one thing you can do. You can apply temperature control and just trace the maximum rate line. The other thing we can think about is, well, over here, why do we allow this long, slow time to reach the maximum rate line? Why don't we jump on the maximum rate line as soon as possible? So what we could think of doing is blasting this reactor with steam initially to jump onto the maximum rate line as soon as possible. So we can say blast steam in until we reach here. So as we blast steam and raise the temperature, the system will get pushed up here. The system will be reacting also, and the conversion will rise, and then we'll end up here. So we try and meet the maximum rate line there, and then we apply heating and cooling again, and we stay on there. So even though in terms of this graph, this line looks longer, right? This line looks longer. There is, this path is shorter in terms of time, right? Pushing ourselves up here onto this point quickly and staying on here. This might be 20 minutes, whereas this route might be 1 hour, right? So this is again where we are trying to be clever by understanding nature, right? We understood nature by getting those kinetic rate constants and constructing these isorate lines. So we've learned our thermodynamics, our kinetics, we've constructed this plane, and now we can think about doing clever things with our reactors and navigating this plane to get the best possible engineering out of it, right? To get the lowest possible time to react. Here again, some economics questions will arise. You can compare these two and say, well, in this case, I only need to do cooling, right? In this case, I just let it react and then I just keep cooling, right? If it does go below the temperature, then I just stop cooling. It will go back by itself up there, and then I just need to keep cooling it down. So I just need to have a cooler in this case, right? Or a cooling jacket. In this case, where I'm trying to jump on the maximum rate path line quickly, I need additional equipment. I need to add in heating equipment as well. So there it's an economics question. Is the saving of this 40 minutes, is that worth? So if you factor in a saving of 40 minutes for every cycle for the whole year, and then what's the cost of that heating equipment, and you compare those costs, and then you decide whether or not to implement that. So that's the kind of balance that you get between design and fundamentals, and that's how you design these reactors. Okay, any questions or comments there? So that is pretty much it for this section. There is another section also related to energy about the nonlinear dynamics aspect. So there's interesting things related to the multiplicity of steady states. So there are some questions in the same tutorial on that. We didn't get to cover that in today's session, but work through those, and we'll cover it in the next tutorial. So those questions with G and R, we didn't as yet talk about that. That's another important thing to talk about. But do practice these problems. So be sure you are able to follow the logic about drawing these lines and figuring out where to stop and where to start. So in the questions in the tests and exams, what we look for is correct application of the principles. We know you can draw these lines and all that, but do you know where to stop and where to start? And those are the really important design decisions, right? So be sure that you can follow the logic and how it changes when the reactor type changes and all that kind of stuff. Okay, any questions or comments there? Okay, if not, that's it for today. Thanks everyone. See you in the next one.